Okay. So this is part 2 because we're not counting the other thing as really a part 2. That was more like a 1.9, like the Rogue One Star Wars movie. So what we're doing now is we are waiting for a few more people to return, so we're going to do another application of monovariance to a Fibonacci game. So this game is currently being analyzed by one of my thesis students at Williams. So we do not yet know what the winning strategy is. We do not know how the winning strategy depends on the number. For each number, there has to be a winning strategy. And the question is, what is it? So a lot of this is very much open. Did we do Zeckendorf's theorem last time that you can write any number as the sum of non-adjacent Fibonacci's? Yeah. OK, so good. So we can recall Zeck's theorem. Any integer is a sum of non-adjacent Fibonacci numbers. I could do 2018, but that would take a long time. So I'll start with the Fibonacci numbers are 1, 2, 3, 5, 8, 13, 21, 34. And so if I give you a number like 44, I take the largest Fibonacci number less than or equal to. This is the greedy algorithm. I'm left with 10. What's the largest number less than or equal to 10? That's Fibonacci, it's 8. If I could have taken 21, well, then I would have had two adjacent Fibonacci numbers, and then instead of using them individually, I would have just used their sum. So now I'm left with 2. I just take the 2, and that's my answer. And none of these are adjacent, because if they were ever adjacent, I would have had, OK. And I'm having the recurrence relation fn plus 1 equals fn plus fn minus 1. So here's the game. I start off with a bunch of boxes for each Fibonacci number. So I will have the 1 box, the 2 box, the 3 box, the 5 box, the 8 box, the 13 box, etc. So to make things a reasonable length game, let's say I start off with 12 ones. And I'll have 0 everywhere else. And on each turn, I have two things I can do. I can combine an fn and an fn plus 1 and make, maybe I'll do an fn minus 1, and make an fn plus 1. Or I could split a doubled Fibonacci number. If I have 2 at one spot, I can write that as fn plus 1 plus n minus 2. So for instance, if I have 2 8s, that's 16. That's the same as 13 plus 3. If I have 2 5s, that's 10. That's the same as 8 plus 2. So the index is 1 higher above and 2 lower below, except if I have 2 2s. And the reason is there really should be 2 1s. But I'm starting the Fibonacci's with just 1 1. And so unless n equals 2, in which case 2 2s becomes 1 1 plus 1 3. And then the goal can be whomever moves last wins. So when we start off like this, we have 12 ones. There's only one thing we can do. The first move, we have to combine 2 1s and make a 2. Right? So I have 12 1s and nothing anywhere else. So my only possible moves is I can combine 2 adjacent Fibonacci numbers and make the next one. Or I can take a doubled number and split it. I can't split 1 into something negative. So I really have to basically say 1 plus 1 is 2 and get my next Fibonacci number. So I should probably modify this as well. And I basically say just 2 1s becomes 1 2.
Why don't you just have the 1 and then you have the same number?
I'm sorry?
Why aren't you using 1 1 2 3 5?
I'm starting off with the number 12.
I know, but why aren't you using 2 1s in the Fibonacci? Why are you using 1 1 2 3 5?
Oh, because if I have 2 1s,
Yeah.
I no longer have a unique decomposition. if I have two ones, if I have an extra one here, when I'm trying to decompose the numbers as sum of non-adjacent Fibonacci's, which one do I use? And so it causes a little bit of an issue. So we're going to just say we only have one. Okay. So we're playing a Fibonacci game using monovariance while we wait for everybody to come back from the meetings. So the way it works is you can combine two adjacent Fibonacci numbers and make the next number, or you can take a doubled number and split. So if I have 2 8s, that's 16. And I can write 16 as 13 plus 3. You have to be a little bit careful because with 2 2s, it's a 1 and a 3. So if I start off with 12 1s and nothing else, there's only one possible move. I have to combine 2 of the 1s and make a 2. So after my first move, I now have 10 1s and 1 2. I now have 2 moves. I can again take 2 1s and make another 2, or I can combine a 1 and a 2 and make a 3. What would you like to do? I will combine 2 1s. And so now we have 8 1s and we have 2 2s. Do you want to combine more 1s, or do you want to combine a 1 and a 2, or do you want to split a 2? So we'll alternate. So I did the first move, I combined. Then you did it, so that's my turn. I will combine a 1 and a 2 and make a 3. So this becomes a 7, this becomes a 1, and this becomes a 1. And we can check, does it still add up to 12? 7 plus 2 is 9, plus 3 is 12. So now it's your turn. You can combine the 2 and the 3 and make a 5. You can combine a 1 and a 2 and make a 3. Or you can take 2 1s and make a 2. What would you like to do?
Sorry, can I just ask
Sure.
Whoever moves last wins. The last one to do what?
Whoever has the last legal move. The game will always terminate to a point where you no longer have a legal move. And we'll see something interesting when the game terminates. So what would you like to do? Combine the 2 and the 3, combine the 1 and the 2, or combine 2 1s? Combine 2 1s. So this 7 I can now actually turn into a 5 in a very nice way. This one becomes a 2. And it still adds up to 12. So it's my turn. I'll take 1 2 and 1 3 and I'll make a 5. So this becomes a 1, it becomes a 0, this becomes a 1, and it still adds up to 12. So you can combine a 1 and a 2 and make a 3, or you can combine 2 1s. What would you like to do? I'm sorry?
Just taking out but you can't put a 1 and a 5 together.
You can't put a 1 and a 5 together. So what would you like to do? Combine 2 1s. So this now becomes a 3, and this now becomes a 2. Yes. So 5, 6, 7, 8, 9, 10, 11, 12 still adds up to 12. I will take a 1 and a 2 and make a 3. So that becomes a 2, that becomes a 1, that becomes a 1, 8, 9, 10. So it's still 12. So now it's your turn. So 3 and 5 becomes an 8. And now I will take the 2 2s and make a 1. Well, let's see. I've got 2 2s here. I'll take a 2 and a 1 and make a 3. And we're done. And so I would win this game. If I had taken the 2 1s and moved it into a 2, then I would have lost. So you might notice something very interesting about the place where the game reaches where you can no longer move any further. So we've got 12 is 8 plus 3 plus 1, which is the Zeckendorf decomposition. So when you play the game will always end in the Zeckendorf decomposition. And there's a lot of things you can do. You can actually prove that among all decompositions, the Zeckendorf decomposition, no other decomposition has fewer summons than the Zeckendorf decomposition. So for instance, if I give you a number like 16, I can write 16 as 13 plus 3. I can write 16 as 8 plus 8. So both of these are decompositions of 16 in terms of sums of Fibonacci's. This is the Zeckendorf decomposition. No adjacent terms, and each term is used at most once. This is another decomposition. Another way of writing 16 is I could write 16 as 5 plus 5 plus 5 plus 1. Of all the decompositions, none has fewer summons than the Zeckendorf. I won't go through the proof, but the proof actually involves associating a monovariant to the sum of the indices, essentially, for your decomposition. And you show that as you continue down here, you only move in one direction. And so since you will always end in the Zeckendorf decomposition, it will have the fewest number of summons. So I'll send, if people are interested, a brief write-up. It's about a paragraph as to how you prove that the Zeckendorf has the fewest number of summons. But it comes down to, can you find a monovariant? I don't want to do it now just in case anybody wants to think about how would you associate a monovariant to the indices. But this idea of a quantity that moves in only one direction is incredibly powerful. So we can actually prove that when you play the game, if you're not in the Zeckendorf decomposition, then you either have two things that are adjacent and you can combine, or you have a number doubled up and you can split. So as you're playing the game, if you're not in the Zeckendorf decomposition, there's always a move that you can possibly do. You just have to prove that you can know that you can't somehow keep cycling among a couple of states, that you will always eventually migrate to the Zeckendorf decomposition, so the game is well defined. So instead of tossing a coin for the Super Bowl as to who gets to decide if they want to kick or receive, you could actually have teams play the Zeckendorf game, and get a little bit of mathematics into the houses. So my question to you is, who has the winning strategy as a function of the number? So my thesis student has a couple of conjectures for some small cases. She and another one of my students have written some really interesting code to explore all the possible games. And the number of games grows very rapidly. So for those of you who are doing any computer programming, just trying to have the students enumerate all possible games for small numbers is highly non-trivial. Okay. So what I want to shift to now is one of the most important applications of calculus. And to do it properly, it's actually calculus plus linear algebra. But in the case we're doing, we only need to work with 2x2 matrices. And we can even avoid doing 2x2 matrices by just looking at, we're solving a system of two unknowns with two equations. And you can always just do the game, well, let's write one in terms of another, substitute and solve. So if you don't know linear algebra, you can avoid having to do it. In terms of applications, this is one of the most important applications of mathematics. It's trying to figure out what is is a proposed relationship satisfied by the data or not? So initially, this is called the method of least squares. And it's going to lead us to linear regression. So the goal is to try to find the best fit line that describes the data. The problem is most relationships in the world are not linear. And the method of least squares, linear regression, only works for linear relations. So what I will first do is I will show you how to find the best fit line to data. And then I will show you that it's actually not so bad. That even if the relationship is not linear, we could actually still use this to find the best fit curve if it's of a certain form. And so the idea is, if you have a bunch of data like this, you want to try to find the best fit line that goes through the data. And the point is, if you have this best fit line, you can then try to extrapolate, well, if my input was now over here, what do I think my output would be? So it's the predictive power. So you have essentially the relationship y is equal to ax plus b. And you observe, say, x1, y1, all the way to xn, yn. And we want to find what's the best fit line. So as soon as you talk about best fit, you have to introduce a metric. How are we going to say how good of a fit is? So any thoughts as to how you might measure how good of a fit something is? So difference from the line from the point. So let's say we want to do difference from the line and the point. So I have 2 points here. Okay. Does everybody know what the best fit line is through these points? So that is the best fit line. Well, let's check. So here, my errors say -3. And here, my error is +3. So my errors cancel. And I have a perfect prediction. We clearly do not want to allow this to count as a good fit. So we just played a Zeckendorf game using monovariants, and now we're shifting to linear regression and the method of least squares. So we're trying to find, if you observe some data, what's the best fit line. So we propose some type of linear relation. This is extremely restrictive. Most things in the real world are not linear. So we'll see later why this is not that much of an assumption. And we observe some values, x1, y1 through x and y, and we believe y equals ax plus b. And the first suggestion was, well, what do we mean by best fit? Let's just look at the distance from the line. And here, since I'm going down, and here, since I'm going up, the sum of the differences will be 0, and that line will have as good of a predictive value as the line connecting them. We do not want to have multiple best fit lines. And clearly, we do not want to have this line connecting them with 0 error in any reasonable way of measuring error being as good as this. So we need to modify the notion of measuring error. How should we modify it? So one is to square it. What else could we do? Absolute values. So there's 2 candidates. There's the absolute value camp. So we'll call this E1 as a function of a and b. So my error as a function of a and b is just going to be the sum, I goes from 1 to n, of yi minus axi plus b. So that's just looking at what I observe minus what I predicted. And we've already seen that this is really bad because positive and negative errors can cancel. So now we have 2 other candidates. We have E2, which will be the sum, I goes from 1 to n, of the absolute value of yi minus axi plus b. And we have E3, which will be the sum of the squares, I equals 1 to n of yi minus axi plus b squared. So in the words of Monty Python, the first one is right out. Right? We're not going to consider just the unsigned errors. But we have 2 reasonable candidates, absolute value and squares. Who votes for absolute value?
I do. I know it's not what we use.
Okay. I'll vote for absolute value. Who votes for square? I'll also vote for square. So both of these have something in their favor. What's really nice about the absolute value is positive and negative errors are treated equally. And 2 errors of size 1 is equivalent to 1 error of size 2. Over here, when you square, 2 errors of size 1 is very different than 1 perfect point and 1 error of size 2. The error of size 2 then squares to an error of size 4. So the problem with squares is 1 or 2 data points that are just a little bit off have a huge impact and will greatly adjust the shape of the line. So I like to say if I am hired, I like to use squares. If I'm doing the hiring, I want them to use absolute values. It turns out it's a lot easier to solve the problem with squares than with absolute values. And it comes down to the fact that I was originally told I should be doing calculus enrichment. So what's the difference between these 2 functions?
You can minimize the error with the second one, right?
Well, we can minimize in both cases. I can vary a and b and see which is smallest.
It's easier to find the derivative.
Yes. This function is not differentiable. So the derivative doesn't exist to find. So because this function is not differentiable, you can't use calculus. Here, calculus is available. So the reason I love to do this whenever I teach calculus is to give the students an idea of why are we spending our time learning calculus? What are the applications? Well, here's one of the biggest applications. I want to find the best fit line. If I use this, I now have a function of two variables. If I use this, there are techniques to find the minima, but they're very complicated because it's not a differentiable function. Now, unfortunately, this is a function of two variables, not one variable. So I have to teach you multivariable calculus. So fortunately, it can be done in about a minute. Now, this is not going to give you the entire course, but essentially, what you can do in multivariable calculus is, if we're taking derivatives of a function of several variables, we take what's called a partial derivative. And for partial derivative, it means hold all the other variables constant and imagine just one variable is moving. So let's say in calculus we have a function f of x. Maybe it's 3x squared plus 4x. Then we might write df dx, I'm using the d notation, will be 6x plus 4. Now imagine I give you a function g of xy is going to be x squared y cubed plus y, let's do it, x, y plus y. So now, if I want to take the derivative of this function with respect to x, I'm going to imagine y is a constant. So I will write this as a slightly different kind of d. So this is read partial f, partial x. So the derivative of f with respect to x, holding all other variables constant. And so y is now a constant. So what would be the derivative of the first term? 2x y cubed. And the second term? Y. And the third term? 0. So that's partial differentiation. Then let's say I have a function in one variable and I want to find the maxima and the minima. How do you find maximum and minimum in one variable? You do two things. You check the endpoints and you check the critical points. And those are the places where df dx equals 0. It's the same in several variables. You check the boundary. And 2 is you want dg dx equals dg dy equals 0. So imagine you're at a critical point. That's a place where both the derivatives vanish in both directions. So infinitesimally, if you're moving in any direction, how should things be going? Well, now we have second derivative tests and third derivative tests. Things get a little bit complicated. Let's go from another point of view. These are finding candidate points. Let's imagine you're at a maximum. So if you're at a maximum, no matter what direction you go, the function can't get larger. So if you move in just any one direction. So the simplest thing is, let's say I move just in the x direction. The function can't get larger. So df dx has to be 0. Because if it was positive, my function would be getting larger. If it was negative, I'd be getting larger if I moved in the other direction. So if I'm at a critical point, if I'm at a maximum or minimum, df dx has to be 0. Similarly, now if I move in the y direction, I would also have to get 0. So this hopefully convinces you that these are the candidate points. It doesn't prove that if these equal 0, you'll be at a maximum or minimum. It's just a candidate. If you think back to calculus, we have this terrible function, h of x is x cubed. And if you plot it, it doesn't have a maximum and it doesn't have a minimum at the origin. But its first derivative vanishes at the origin. So just because the derivatives vanish, it doesn't mean you have a maximum minimum. It means you have a candidate. This is a place to investigate. Similarly, over here for multivariable functions, these are candidates. So let's go back to what we're looking at over here. Here's our error function. do you agree that there should be some value of a and b that minimizes this sum? Yes. Sure.
So as we're moving along, I thought maybe I would get to it, and I don't understand. It's clear why the first derivative for the quadratic one is 6x plus 4.
Right.
No problem. When we go to find the partial derivative of f with respect to x.
Of here?
No, sorry.
Partial derivative. Oh, this should be g. Sorry, this should be g.
Oh,
sorry.
Thank you.
Yes.
So we get this 2xy cubed plus y.
Because imagine y is just a constant. If you want, think of the function as g of x comma, and I'll put in pi. It'll be x squared pi cubed plus pi x plus pi.
No, I understand.
Okay.
What I don't know or haven't, so do you still have to do the partial with respect to y as well?
Well, you could do that, but right now I'm just asking how is my function changing if I change x?
Okay.
I'm keeping y fixed. So this is basically saying I'm standing here.
You're only looking in one
I'm
direction.
only looking in one direction.
Okay.
Now what you could do is, well, what if I want to move diagonally? And then I would somehow want to express that in terms of the partials in both directions. So I'm doing a very special case. I'm here. I'm only allowing myself to move, left and right, or forward and back.
Got it. Thank you.
Yep. And so it's enough because it gives me a good condition to check for maximum and minima. So you're absolutely correct that there's a lot more to the theory. I'm trying to do the bare minimum of multivariable calculus needed for.
Just checking I did
Yep.
something.
Yep. So there are other directions you could check, and it becomes a very interesting question. There are times when the derivatives can exist along the coordinate axes, but the function is not differentiable. And you can have strange stuff happening. I'd use stronger words, but this is being recorded. But these are giving you candidates.
Yeah, so if there is a maximum, it's got to make this.
It has to satisfy this. But just because it satisfies it. So this is necessary, but not sufficient.
Right.
So much of life is like that. So this is pruning where you need to look. And if you're lucky, from physical grounds, you can prove that a maxima has to exist. So let's look at this function here. Imagine I have a finite amount of real-world data. Send A and B off to positive infinity or negative infinity or something like that. Right? If you let B go off to infinity, you can make this error incredibly large. Same thing with A. So without loss of generality, we can say A and B are at most a quadrillion in absolute value. Because if it's larger than that, the error will be huge. And the error will be much smaller than just taking A and B to be 0. So what you can do is you can prove that it's enough to consider the absolute value of A and B less equal to some big number. Because we have finite real-world data. And so now we are living inside a square. And there's a result from real analysis that says if you have a continuous function on a big square, it takes its maximum and minimum value. So this goes back to what we talked about earlier, that a lot of times mathematics will tell you something exists without giving you any idea of how to find it. So the result from real analysis tells us a maximum exists, a minimum exists. No idea where they are, but they exist. So your search is not in vain. Okay? So before you spend too much time looking for something, it's nice to know that it will be there to find it. Any George Carlin fans here? So my kids love the airline routine, and because be careful, I won't mention anything about the profane words they know. But he has a nice bit where the stewardess is telling you when you land, please check your immediate seating vicinity for any items you may have brought on board. And George Carlin goes, I may have brought on board my grand piano, but I didn't, so I'm not going to look for it. I'm going to look for the items I did bring on board. And so when we're looking, it's nice to know that the object of our search is there. There will be some value of A and B that will minimize this. And we only have to check the places where the partial derivatives both vanish. So is everybody happy now with using error 3 and looking for places where the derivative simultaneously vanishes? Okay. So even though we're doing multivariable calculus here, we're really just doing one variable calculus twice. And then it's going to lead to algebra. So it's going to allow people to review solving systems of equations, which is something they should have done before calculus. But it's going to have a real application. So let me do the algebra. So we will go back to our error as a function of a and b is going to be the sum, I goes from 1 to n, of yi minus axi plus b squared. Is everybody comfortable with the summation notation? It means first take I equals 1 squared, then take I equals 2 squared. So let's calculate the error and take its partial derivative with respect to a. So what is a little bit confusing is x and y are not the variables here. A and b are the variables. X and y is the data. So the derivative of a sum is the sum of the derivatives. You prove that that's true for partials as well. So we have a sum, I goes from 1 to n. Now we take the derivative of this whole thing with respect to a. So the 2 comes down. We then get yi minus, I'm going to just spin out the minus sign, axi minus b. And now we take the derivative of this with respect to a. So what's the derivative of this whole expression with respect to a? Negative xi. And that's supposed to equal what? 0. Now we take the derivative of E3 with respect to b. And I'll send you notes that have all the algebra here. I goes from 1 to n of 2 yi minus axi minus b. And now we take the partial with respect to b, and what do we get? We get negative 1. And now it's just a function of doing algebra. So amazingly, of all the stuff I've ever done mathematically, my most downloaded item is the notes I've written on this when I was a postdoc at Brown about 15 years ago. All right, so let's do the algebra. So here, does everybody agree I can drop the 2's? And I can drop the negative signs? So I can no longer say these are equal. I'll say it's leading to this because I'm now dropping the 2's. I'm dropping the negative sign. OK. So now let's look at what I have here. I have the sum of xi, yi. Can I write just sum to save time? Do I have to write 1 to n? Is this OK? So I'll write the sum of xi, yi minus this sum minus, I'm going to put those on the other side, will equal the sum of xi squared times a plus the sum of xi times b. And I'm just moving these over to the other side. So I have a minus axi squared becomes an xi squared a. The other one will be a sum of yi is the sum of xia plus the sum of 1. OK? Is everybody comfortable with the algebra? Did I make a mistake? Oh, there should be a b over here. Thank you. Now is everybody comfortable with the algebra? So over here, if I multiply this out, let me just do one of them. I have a sum of yi minus axi minus b. So this is the sum of yi minus the sum of axi minus the sum of b. And since this equals 0, then I get the sum of yi is the sum of xi times a, I'm just putting it on the other side, plus the sum of 1 times b. This is a number. It's a number from your data. This is a number from your data. I can pull the a out because a is multiplying every term in the sum, just factor out the a. B is multiplying every term in the sum, I can factor out the b. Can I write this in matrix form? Are people comfortable with 2 by 2 matrices? So if I write this in 2 by 2 matrix form, I would have the sum of xi squared, the sum of xi, the sum of xi, the sum of 1, acting on AB equals the sum of xi yi, the sum of yi. If you don't like the matrix form, you can leave it like this. It's 2 equations and 2 unknowns. So if you remember your matrix algebra, you can actually solve for a and b in terms of the inverse of this matrix. This leads to a natural question. When is this matrix invertible? when will you be able to solve for A and B? It turns out you will always be able to solve for A and B unless you do one very, very stupid thing. Our goal is to try to figure out how y depends on x, right? And we believe y linearly depends on x. There's one thing we could do, one choice of values of x that would cause problems. And as long as we stay away from that choice, everything is fine. If every value of x is the same, we have problems. We should have problems. We're trying to figure out how does y vary with x. And we're only going to observe one value of x. So one of two things happen. All the values of y are the same because we have perfect precision in our measurements, not happening. Or, even worse, they're going to fluctuate. We'll have the same value of x giving us multiple values of y, in which case everything comes crashing down. If you want to see how y varies with x, vary x. Keeping all the xi's constant and the same is bad. So if you've done some basic probability, it turns out that the determinant of this matrix is the variance of the xi's. So as long as the xi's aren't all the same, the determinant will be non-zero, and it will be invertible. It's not worth going into this now, but it's just nice to know that the method will always work, and this will lead a solution. It gives you a as a function, I'll call it some function of the xi's and the yi's, and b will be some other function of the xi's and the y's. And you get an explicit function from solving these 2-by-2 equations and two unknowns. It's incredibly powerful. And so the best fit line, you actually just do a bunch of sums like this, and then multiply both sides by the inverse of the matrix, or say, well, look, let me solve for A in terms of B, substitute, then I'll get B, then I'll substitute back and get A. So we can find the best fit line in closed form. You give me the data, and I know the answer. If we want to use absolute values, you actually have to run a simulation. And it's very complicated to find what the best value is. So this allows us to solve the very special case of a linear equation. Most things in the world aren't linear. So you want to step back and see, where do we really need linearity? We need linearity in a very interesting way. It just has to be linear in the a's and the b's when we take the derivative. So over here, when I had this functional form, I could have had a different functional form so long as when I take derivatives, I have something that's linear. So for example, let's say I want to try to find the best fit parabola. So instead of doing ax plus b, I'll do maybe now my error as a function of a, b, and c is going to be the sum, I goes from 1 to n, of yi minus a xi squared plus b xi plus c squared. And now when I take the derivative of this with respect to a, I'll get the sum twice this whole expression to the first power. And now when I take the derivative with respect to a, because a only appears to the first power inside here, I'll then just get xi squared.
It's really the same technique.
It's the same technique. So what you can really do is yi is a1 f1 of x. Sorry. Y is a1 f1 of x plus a2 f2 of x plus dot 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 plus ak fk of x. And the f's don't have to be linear. It just has to be a known in front of them that is linear. So anything like this, I can then find the best fit values, but I would need to know what the f's are. And the reason is, here, it's not the x's and y's that are varying. The x's and the y's are known. It's the best fit parameters a and b that are varying.
All right.
Yep.
Just back to solving for a and b.
Yes.
So the inverse of the first matrix, gets multiplied.
Yep. So for instance, if I give you, let's just write down. So let's say I give you a matrix.
Those are numbers that we can get. The sum.
Yes.
Sorry.
Right.
Okay.
So if I give you the matrix, say, alpha, beta, gamma, delta, the determinant of the matrix is, let me use, see, the problem is I've already got A's and B's. I'll use capital letters. A, B, C, D. The determinant is AD minus BC. And so the inverse matrix, it's 1 over the determinant, AD minus BC. Then I flip the diagonals, so it's D, A, and then it's negative B, negative C. And when I multiply, I'll get AD minus BC over that, which is 1, negative AB, positive AB, it's 0. So for the 2 by 2 case, we can explicitly write down what the inverse matrix is. And then we can use that to solve here. For a 3 by 3 or 4 by 4, there are formulas for the inverse matrix. They just become more involved. But the point is that it's not a bad equation. The computer can easily write down the inverse matrix and do the coding. So this works very nicely if it's a linear relation in terms of the actual dependence on x can be nonlinear, but it's got to be a linear times that. So how many of you are familiar with Newton's law of universal gravity? The gravitational attraction between two objects. Bigger pulls. And so the force between two masses, if this is M1 and this is M2, they're pulled towards each other, and they're pulled along the line connecting their centers. The force is Newton's universal gravitational constant, M1, M2, over the distance between them. Okay? Let's assume that we fix M1 and M2. Then the force should basically be some constant over, let's say, r to some power p. Or if you want to use notation that's similar to what we had before, I'll do it as alpha and beta. And I don't know alpha and beta. So I believe that the force is some power, is related to some power of the distance between them. I think it's square, but I'm not positive. And if there's some proportionality constant, I'll assume the two masses are fixed. It's essentially, G is driving what alpha is now. And for the longest time, it was actually an extremely difficult problem to determine what G is numerically. Anybody here ever teach a physics class? Okay, they have Cavendish's experiment, where you have two very, very large masses, connected on like some kind of wire, I think attached like this. This is Cavendish. And then there's like small masses around it that it's like torquing towards. And over a small amount of time, you can measure how much it's moving and use this to determine what the gravitational constant should be. It's extremely difficult to calculate what G is. So let's assume we have this kind of proposed relationship. We think that the gravitational attraction should be proportional to the radius to some power. But we don't know the power, and we don't know the proportionality constant. But let's say we do a bunch of measurements in the lab. We would love to use the method of least squares to figure out what alpha and beta should be. The problem is it's not linear in them. We need things to be linear. So any thoughts as to what we could do so that we could then use the method of least squares? Take logs. Excellent. Who said that? So logarithms are constantly viewed as students as a topic done by evil teachers who have nothing better to do than make them suffer. And there's no real reason why anybody would ever use logs. The whole point of logarithms is you can convert from one type of relationship to another. So let's say we start off with f equals beta divided by r. I'm sorry, I had alpha up top. Alpha over r to the beta. I think I put things in the wrong way. I apologize.
So is the purpose that you're saying we're going to go from that bottom to show the top?
Well,
I guess I'm a bit confused.
so this is what we know is the truth.
Yep.
Let's say we think some kind of relationship like this holds. We don't know what the value of the top is, and we don't know that the exponent is 2. So let's say
I'm
we'll...
saying before you knew that first equation.
Well, I'm saying, let's say we're positing some kind of relationship of this form, that we think the attraction should be proportional to the distance.
Okay.
And so that will give us something of the form alpha over r to the beta. And then we're going to go to the lab and we're going to measure different attractions.
Because you don't already know that first equation.
Right. I mean, if we knew the first equation, there would be no need to try to figure out what is this. And then the question is, how could we figure out an exponent of 2? Because this is highly nonlinear. What we did over here is it's got to be linear in the unknown. So I have here a outside the xi. Now I would have a as the exponent. So I've actually flipped the alpha and the beta. So let me flip them back. I'll do it as, beta r to the alpha. So we have some proposed like this, beta r to the alpha. And in fact, we think alpha is probably negative. The further objects are, the less attractive they will be. So now let's let y be the log of f. Let's let x be the log of r. So if we take the log of both sides, we get the log of f is the log of beta plus alpha log of r. Or y equals log of beta plus alpha x. Or, if you want, y equals ax plus b, where a is just alpha and b is the log of beta. So if we believe that there is a force law like this, we can actually still apply the method of least squares to find the best fit values of alpha and beta by doing this logarithmic change of variables. And now we apply the method of least squares to this linear relation. How many of you are familiar with Kepler's 3 laws? So Kepler had 3 laws of planetary motion. What's the first? No, that's Newton. So the first law is basically planets move in elliptical orbits with the sun as one of the 2 foci. The second is equal areas and equal time. So the amount of time we spend out over here and the amount of time we spend over here, if those 2 times are equal, then the area swept out is equal. And then the last one, yes, this is the worst one. It's like something like the period squared is proportional to the semi-major axis. I believe it's cubed. I believe its period squared is proportional to semi-major axis cubed. Another way of looking at it is, the period is equal to some constant times, if we let, we'll use S for the semi-major axis, to the 3/2. Well, initially, this is not something where we can use the method of least squares, because we don't know that this is 3/2. So we would have to guess another kind of power law relationship like this. And so you can guess what's the power law relationship, and then you can do the method of least squares, and you can see what's the best fit exponent. So when I teach the method of least squares, I use planetary data. When I started to do this, there were 9 planets in our solar system. We no longer have 9 planets, we now have 8, because Pluto has been downgraded. This really bothered my son. And in fact, I know somebody who knows the person at the International Astronomical Society, whatever it's called, who was the one who officially hit enter to officially downgrade Pluto in the database that matters. And he said he didn't want to do it. But he was told Pluto is no longer a planet, you have to change its status. But so even if you use 8 data points, you can actually observe and you get a beautiful fit for 1.5 as the ratio. And so the power of the method of least squares is you can attack a variety of challenging problems. And the relationships don't have to be linear. If you could only find linear relations, you'd be in trouble, because most things in life are not linear. This allows you to talk to your students about why are we doing logarithms. Well, sometimes logarithms are done just to make things a little bit more convenient in terms of the scale you look at. So does anybody know any scales in the real world where we use logarithms that students might be aware of? Richter scale for earthquakes. Sound, decibels. And I think there's one other that they might know, but they'd have to be taking a certain type of science class. I think a chemistry class. Yeah, pHs. Those are the only ones I can naturally think of in terms of logarithmic scales. But because we can do these conversions, we're in great shape. I'm sorry? No. The speed of sound? No, I think Mach 1 is the speed of sound. Mach 2 is twice as fast. Now, the speed of sound, interestingly, is not always the same value. It depends how high up you are. But those are the only 3 logarithmic scales that I can quickly think of. Earthquakes, decibels, and pH balance. But all you're really doing is you're just converting how the data is presented. You're not really fundamentally changing things. So here, by doing a logarithmic change of variable, we can actually now use the method of least squares, which needs a linear relationship. So another way of saying this is a lot of nonlinear relationships, not surprisingly, if you adjust your coordinate system properly, look linear. Okay, so I think this is a good place to stop for a little bit. I will upload the next file. If I can turn this off.